Hi, in this video, we're going to discuss how to create a neural network with TensorFlow. So what is TensorFlow? TensorFlow is a free software library that can be used to create neural networks using some basic Python programming commands. TensorFlow is used by many different companies for many different AI applications. For example, Spotify uses it to make personal recommendations. Google uses it in several products such as search and translations. There are some great features of TensorFlow that you'll be able to use, such as easily managing training and testing data, creating flexible models, easy access to model metrics, and best of all is that most of this works with standard templates, so there's very little coding that is needed. Let's revisit the temperature conversion problem you looked at earlier. Recall that traditional programming will use an input into an algorithm to calculate a final output. In the machine learning environment, the problem looks different where the inputs and outputs are known, but the algorithm is unknown. Given this model and equation, we would use weights and biases to come up with values to predict our output. So let's take a peek at how this simple model would get implemented in TensorFlow. This is the code to implement the model. It's important to know that much of this code will be given to you. In this course, you'll be looking at adjusting model parameters on existing code, so don't worry too much about all of the syntax. With that said, let's take a look at this piece by piece. The first thing you'll see is the training data. For this problem, we have a known Celsius value as the input, and the output is a known Fahrenheit value. These will be the values for our training data. Each position in the list has a corresponding position in the output list. For example, an input of -10 degrees Celsius will correspond to 14 degrees Fahrenheit. Next, create the model. In this course, you'll be using sequential models, which is essentially a model that calculates values layer by layer, like you saw in the neural network. Here you have one dense layer. Remember, a dense layer is simply a layer of nodes where every node is connected to each node above and below. The unit value tells the model how many nodes to use in that layer. Remember, the nodes represent different variables that are used to fit the model. For our temperature conversion model, we said we only needed one node. But as you build more complex models, you'll have a chance to adjust these values and optimize your model. The input shape tells the model how many input values to expect for each case. In our model, we only need one input representing our degrees Celsius, but as models get more complex, we'll update this value accordingly. The model compiler specifies how the model will determine the loss or error when it tries to fit the data, as well as how far to go before the error is acceptable. The loss is essentially the difference between the calculated model value and the known output value. For example, if the model input was 100 degrees Celsius and the model calculated the output to be 211 degrees Fahrenheit, the loss would be 1 degree. Depending on the model that you create, different loss calculations and different thresholds will be used. However, in this course, we're not going to get into explaining these too much. You'll always be given these parameter values and commands. Finally, the model fit command is where the computer fits the training data to the model. Essentially, this is where the model is created, and this is the step that takes the longest. Notice that the input and output data are listed first, followed by the number of epochs to run. Remember, an epoch is one complete run through of the data. So this model will run completely through the data 500 times and make adjustments to the weights and biases as it goes. As mentioned earlier, much of the code will be given to you, or at least available to copy from previous examples and exercises. A lot of what you'll look at doing is adjusting model parameters, highlighted here in red. As you go further, you're going to see different models, and those will have different parameters as well. To see the results of the model, you need to print values with a few commands, including the command to use the model to predict the value for 100 degrees Celsius. Notice that the prediction is pretty good, but not exactly 212 degrees. Using weights and biases, the conversion equation would be 1.83 times degree C plus 28.3. This is pretty close to the actual value with just a little bit of training data. So as mentioned earlier, your job is going to be to update model parameters. So what if we updated the model from one dense layer to two dense layers with 3 nodes? Will that improve our results? You still have a single input value to produce a single output value, but now you'll have a model with 2 dense layers, each with 3 nodes. Notice that since the layers are dense, each node from the second layer connects to each node in the third layer. The program is nearly identical to the previous one. The only change is the model where you now have 3 layers instead of 1, and a reduction to the number of epochs. Notice that each layer is separated by a comma in the model variable. Only the first layer needs to have the input shape. TensorFlow knows that the input shape of the other layers will be equal to the output shape from the previous layer. The last layer needs to have units equal to 1, representing 1 node in the last layer to be the output temperature. If you have categorical data such as trying to predict cats or dogs, you would have 2 nodes here. We've also decreased the number of epochs to 200 because the added nodes and layers in the model increase runtime significantly. Reducing this to 200 will not have much of an impact, but will shorten the runtime. Notice the output now. The prediction is still basically the same, but the model is much more complex. The number of weights in the first layer increases from 1 to 3, but that number increases exponentially to 9 in the second layer. The end result is still basically the same, a prediction that is nearly correct, but not exactly. Now that you've learned a little bit about TensorFlow, it's your turn to explore.